learned in lecture 6 to do the first problem. And for the second problem is about using GraphX, which will be learned by today's lecture. So please use GraphX to finish the second to do the second problem. And okay, this week and next week, the 2 weeks labs are on Spark, so you can do more practice on Spark. They will help you to have a better understanding of Spark programming and also help you to finish the third project. So I hope that before you begin your third project, you can try to finish the 2 labs first. Okay, so now let's get started about today's lecture. And because last week is a gap, so let's have a review of the chapter 6. First, it's about why we need Spark and why Spark is developed. The major idea is because in MapReduce, the sharing is based on disk, right? So it is not suitable for iterative jobs, because between each iteration, the data sharing is based on HDFS, which means that I/O cost is very high, and it is also not very suitable for interactive problems. And MapReduce is mainly suitable for the batch jobs. So for interactive, such as some auto queries, and for each query, you need to read the data from HDFS to memory once for processing. So it is not very efficient. And that's why Spark you facilitates the system memory to do the big data processing. And it avoids saving the intermediate results to disk, because in MapReduce, after the map tasks, there are a lot of intermediate results generated. So you need to store these results on your local disk, and then in the reducer will fetch these intermediate results from disks. So that's in MapReduce, but in Spark, there's no such cost. And it caches the data for repetitive queries. So for different queries, and the data will be only read from disk to memory once. And for all the other queries, so you just need to read the data based on in memory. So it's much more efficient than reading data from disk. And it's different from Hadoop MapReduce. So mainly Spark uses HDFS provided by Hadoop. Use Hadoop HDFS for storage purpose only. And another difference between Spark and Hadoop is that how to achieve fault tolerance. In MapReduce, it is achieved by redundancy, by replication. So each data chunk will be replicated for 3 times by default. And in Spark, because the data is in memory, so there's no such data replication. And instead, it's called a re-execution. There's a lineage for the execution. And when some data is missing, so Spark knows that how to achieve, to generate the missing data according to the execution plan stored along with the data. So that's the ideas of Spark. And there are 4 major components in Spark right nowadays. The first one is Spark SQL and Spark streaming. So this is for structured data. So the data is represented by tables, schemas. Just like in relational database, right? So you just use tables to store your structured data, and then there's some kind of a SQL-like statements for you to use to query the data. And for Spark SQL, so it means that you don't need to know Spark actually. You just need to utilize the SQL languages to do the big data analysis. And secondly is for streaming data called Spark streaming. And we will briefly touch the 2 components today. And the third one called GraphX is mainly used for graph data processing. And based on your second project, you should already notice that actually MapReduce is not very efficient for dealing with graph data, right? Because if you want to compute shortest path distances, you still need to do many runs given your graph to get the final results. But for different iterations, you always need to store the current results to HDFS, and this is the input of the next round's mapper. And as a result, there are many costs on this data storage into disks. So MapReduce is not very suitable for graph processing, especially for the iterative problems. And another problem for graph is because it's a computation model, it's map and reduce, right? So in map, they also need to read data in kind of sequential read the data from the beginning of the file to the end of the file. So someone asked me if it is possible to not read the files again and again, but do some kind of update for the file in MapReduce. Because MapReduce does not support random access, actually, it's only which means that it is not. I can't say it is not possible, but it's not very efficient, also very difficult to update the existing file on HDFS. So that's why you need to read the file and do the processing and generate a new file, and this new file will be read in the next iteration. But today, when we learn GraphX, you will see how Spark deals with graphs. And it utilizes a Pragel computation model. So if you still remember Pragel, it's not like MapReduce. It is a vertex-centric computation model based on BSP message passing model. So in GraphX, it supports some Pragel operators. So you can utilize these APIs supported by Spark GraphX, and you just need to define the relevant functions. So then you call the Spark Pragel operator. So then GraphX can utilize Pragel computation model to do the graph computation problems. Last one is called MLLib. It's for machine learning algorithms. So in Spark, currently, it has already provided many supports for the machine learning algorithms, such as recommendation, classification, clustering, and some other relevant or regression. Some other many machine learning algorithms have already been supported in Spark. So just need to use APIs to do the machine learning tasks. So for this one, I will briefly introduce it when we learn some machine learning relevant topics in the future lectures. So today we will briefly touch these two and then introduce this one because you need to use GraphX for the third project. For Spark, the most important concept is called RDD, the resilient distributed data sets. So according to the name, so as a side, you need to remember three keywords for RDD: resilient distributed data sets. So resilient means it's fault tolerant, and distributed. So the data in memory is distributed to different nodes in the cluster, and that's why the partitions is used in RDD. And data sets, okay, so definitely it is used to store the data. And based on the RDD, you can have many operations. So these operations are categorized into two types: the transformation operation and action operations. So the transformation operations will returns takes one RDD as input and returns you new RDD. And action will take RDD as input, but it evaluates the RDD according to the operation and returns you a value instead of RDD. So the difference between RDD and value is RDD is the data type in Spark. This new value, well, we can use different languages to fetch the value to see the results. So use the one figure to explain the two types of operations, where you can see this RDD, this is the value, and transformation will take one RDD and give you a new RDD, and action takes the RDD and give you the values you expect to fetch. Pair RDD is one almost most widely used type of RDD in Spark, because by using pair RDD, many algorithms in MapReduce can be transformed to Spark directly, almost directly, because there are map and reduce functions in Spark as well. And it means that in this data, you have a pair, a key, and a value. Okay, and the Spark provides some special operations on the pair RDDs. You can create the pair RDDs according to some transformation operations, and then you can use very different action operations to get some results. So let's see some example. Assume that we have a 3 pairs, 1, 2, 3, 4, 3, 6. And reduce by key, according to the function you give to reduce by key. So it will do the following. So it will do the do the aggregation based on the keys. So for example, it will group all the key value pairs that have the same key. And then based on the function give, here is a sum function. So it will sum all the values for the same key. So as a result, 4 and 6 will be summed together, and you have 2 pairs in the results of reduced by key. Reduce, do the reduction, do a kind of aggregation based on the keys for the values. And group by key also do some kind of aggregation, but it just groups the values together. It returns you a group of values for the same key. And map values works for the values only. It will not affect keys. So for example, map values. And for the given function, it will increase the value by 1. So as a result, if this is the input and output will be like this. All the values in the pairs will have a new value. So this map values. And flat map values, just like what we have learned map and flat map, the difference between map values and flat map values also almost have the similar ideas. So let's look at the function to flat map values, x to 5. So it also works on values only. So 1, 2, and it's from x to 5. So from 2 to 5, and each such value will be combined with a key and generate new pairs. So it's a 1, 2, and next is 3. So 1, 3, 1, 4, 1, 5. So that's for 1, 2. 1, 2 will correspond to the 4 pairs. And 3, 4. So from 4 to 5, there are 2 values, 4 and 5. So it is 3, 5, and 3, 4. 3, 4, and 3, 5. And 3, 6. So 6 is already larger than 5. So there's no output for this key for this pair. And this is the final result. A flat map values. So if it is not flat map values, and it's will be the result will be grouped be split to 2 groups. One for this one for this one. But now, because it's a flat map, so finally it is just a list of key value pairs. You can try to search for the menus to see the different transformation operations, to see what kind of operations you can use to do the tasks that can help you to solve your problem. And for actions, similar to the transformation actions, they also take a pair RDDs as an input, but it generates some values for you. Remember that the result is stored in RDD, but here it is not stored in RDD, it is a value. Okay, although in these slides it looks like they have the same format, but in Spark they have different data types. This is RDD, but this is values. Count by key, to count the number of values for each key. So there's only 1 pair for key 1, so it's 1. But there are 2 values for key 3, so it's 2. And collect as map, so it will return you as a map, storing all the values. Lookup 3 is kind of lookup table. So for the values for this key 3 will be returned to you, which is 4 and 6. And this pair RD operations. By utilizing pair RD operations, you can do a lot of things. Because if you can solve this problem in MapReduce, then you can utilize the MapRDDs to solve the problem in Spark as well. Next is about the partition. I think I didn't explain this concept clearly in last lecture, so try to emphasize this concept again. For partition, so the RDD can be partitioned. So the data inside this each RDD is actually split into several partitions and then distributed to the nodes in the cluster. By default, so Spark will compute a partition for you, just like MapReduce. MapReduce will compute partition for you, compute the number of map tasks for you. So the number of partitions determines the parallelism of your algorithm of the execution, right? So if there are more parallel jobs in the cluster, it means that you can have better efficiency. But anyway, so you can still explicitly specify the number of partitions in the operations, such as text file. And you will read the text file into memory to 4 partitions. So Spark will, according to your parameter, so it will divide the RDD, this text file, into the relevant partitions. But normally we don't need to specify this number because Spark will compute this number of partitions for you. And typically, this is dependent on the number of CPUs in your cluster. So normally we want about 2 to 4 partitions for each CPU in the cluster. And the Spark will try to set the number of partitions automatically based on your cluster, actually. So if you have a cluster with 50 cores, remember it's not nodes, it's 50 number of CPUs. And so at least, if you want to utilize the computation power of your cluster, so at least you want your RDDs to be split into 50 partitions. So each partition can be processed on one computer, on one CPU, right? And probably maybe 2 to 4 times of the number of the cores. So that's about how Spark will compute the CPU, the number of partitions for you. And because all the data in Spark is stored in memory, right? So the size of each partition is determined by the available memory of the one executor on the node. And so how to decide the size of the partitions actually is a trade-off, because if you have very small partitions, if you have many partitions, well, the task will be distributed to more workers. So more workers will be executed in parallel. But the problem is that so this is good for the load balance, because each worker may get similar amount of data. But large partitions, which means the fewer partitions, can allow the work to be done in large the large data chunks, and this can result in the work getting done more quickly on one worker. So because for different partitions, actually there are some other overheads, such as data exchange for the communication, and so it's hard to say how to decide the size of partitions. But I think this is a good criterion. So it's up to the number of CPUs. So this is from the homepage of Spark. So Spark has this advice for us. So it suggests that first try to think about how many CPUs in the cluster is available, and then based on that number, so you can set the partition, or you can just put this job to Spark. Spark can compute this for you, actually. And so if you change this number, which means that there are more partitions for this RDD, right? So there are more parallel jobs in the cluster. But if the performance will be better, it also depends on your cluster settings. It depends on if you have more CPUs available in the cluster. So if so, then it is. Okay. So in summary, well, the Spark is the architecture is like this, and there's a driver program, and the programmer can specify the number of partitions, but Spark can also compute this for us. And for each partition, so for each partition of the RDD, the worker will process this partition, and all the workers will do this in parallel. So you have different ways to do the cluster management, and for each partition, the Spark will automatically push the closure to the workers. So remember, what is a closure? Closure is a function plus environment, and so there's so each operation is kind of a closure, and it will be pushed to the worker for its operation. So this is a whole very high-level picture of Spark. And in last lecture, we didn't finish this topic, so I try to explain this again. It's about shared variables. It's still about the concept of closures. For example, we have this query. We take this query from the standard input. Okay, and then next we want to do a search. We want to find all the lines containing this query, and then we do a count. So in Spark, we can do this page filter to check for each line in this page if this line contains this query, and then we do a count. Okay, remember that this actually is executed in workers, right? So how to do this? Now Spark will push this closer to the workers. And it is called closer because we have the function, and also the function has an external variable, which is query. This query is taken from this standard input. And if there are some partitions, right? So assume there are 4 partitions, then there will be 4 workers used to do this job. And each worker will get a copy of this query. So that's what does it mean? So this external variable will be pushed together with the closer by Spark to the cluster nodes. And well, this is okay if query is not a long string. If this external variable is not too big, then it's fine. But each task will get a new copy. But remember that this is only one direction, so we can push the closer to the node, to the worker. But the update in the worker cannot be reflected, cannot be sent back to the driver function. So the driver does not know if this is updated in the workers. And also the variables must be serializable because this need to be sent out by I/O. So this must be serializable. Okay, so for these shared variables, in Spark, it is like this. So when you perform the transformation actions and use some functions, so Spark always will automatically push a closer containing this function and to the workers that run job. And any variable or data within this closer will be distributed to the worker nodes along with this closer, just like the previous example. And when a function is executed on cluster node, so it works on separate copies of all the variables used in it. This is copied for several times, and each copy is used by one cluster node. And normally these variables are constant, but they cannot be shared across different workers. So there are many copies for the same variable. By doing this, actually there are some problems for the following 2 types of jobs. The first one is once the global variable is very big, especially for the machine learning algorithms or for the graph algorithms. And for example, we have a graph need to be processed for each worker, right? So you need to push this large graph to all the workers in each time, which means this is very inefficient because this global variable is very huge, and you need to create separate copies for this graph and for each worker. And the solution in Spark is that there is a so-called broadcast variable, and you can use this broadcast variable to store this big global variable for, and as a result, so it can be shared across different workers efficiently. So this is for the first solution. Another one, the next problem is like the counter in MapReduce. So in the second project, you are asked to use counters. Well, you can see for counters, it can be shared across different clusters, different nodes. And so it can be used for different kind of statistic jobs, such as to count how many lines, input lines are blank, how many input records have been processed, something like that. But in Spark, closures are just one way. So the closer, the function, and the data are pushed from driver to the worker, but cannot be sent back. And the solution in Spark is called accumulator. And it just shares a similar idea with a counter in MapReduce, so it is more easier to understand. For broadcast variables, as introduced in the previous slide, it's used for the problems with very large shared variable. And it allows the programmer to keep a read-only variable cached on each machine instead of shipping a copy of this database closer with the functions. So you don't need to send this to create a copy for this shared variable and then send this data to the worker every time. But you will cache this data on each node when doing the jobs. So for example, to give every node a copy of the large input data set efficiently. So this for the broadcast variable. And in Spark, there are some mechanisms to efficiently do this broadcasting to reduce the communication cost. And this is one example about how to do use a broadcast variable. So for example, we define a broadcast variable, and this contains one array with number 1 to 3. And so for this broadcast variable, on each work node, and it has it will cache this in each node. And the broadcast variable can also be used can be used when it is required for some operations. Okay. So you can see this example. If you check broadcast value, it will return the value to you. It is one array of type contains some integers. So the broadcast variable should be used instead of the value v in any functions run on the cluster. So you always need to use this broadcast variable instead of the original value, so that this value will not ship to the nodes more than once, just once, and then in next time it will not be sent from the driver to the worker again, and it saves the costs. So that's for broadcast variables to store large, huge shared variables. And next is accumulators. This is much more easier to understand because you already know what is counted in MapReduce, right? So accumulators are variables that only added to through an associative and commutative operation, and therefore they can be efficiently supported in parallel. So it's very important that it is associative and commutative, which means that the order of the operations will not affect the result, right? So if we can change, you can change the order, and you can this can be computed on this node first, and then this node first, and the next, and then combine the result together, or those nodes first, and then this node next, and combine together. So the result will not be affected by the orders of the execution. And they can be used to implement counters or sums, just like in MapReduce. So this is one example. In tasks, the task will do the operations for the accumulator, such as increase the value. And then finally, only the driver can read, can read accumulator's value. So when all the tasks finished, so in the driver, it can check what is the value for the accumulator. And you use Spark context to create an accumulator. And here, so for example, we have a long accumulator. And then we do this job. We parallelize this array. And then, so we can generate an RDD storing this array. And for each array, we use this function to do the accumulation. And so after the job is finished, we can check the result. It's just do sum for this value is 1 plus 2 to 3 plus 4. So the final result is a 10. So this value can only be checked in the driver. So these accumulators. You can also do this by so this just actually exactly almost the same as counters in MapReduce. This is one example in Python. So this is a Python code, a piece of Python code. It is used to count the empty lines in your input file. So you read the input file from maybe from HDFS or from a local file disk, it's okay, and that is loaded into memory as RDD. Now we create accumulator to count the black lines, and then we define a function. So for in each function, in this function, so if the line is empty, then we will increase the number of black lines by value 1. So remember that this function is performed on the partition data. Okay, so for each partition, we use the same function to do the job. So each partition will have results for these black lines. And then finally, the results will be aggregated together. So after all the jobs are finished, after all the data is processed, we can get the final results for this black line. So we can count the number of black lines in the input file. So accumulator provides you a way to send the update in the worker back to the driver instead of just send the closer and the data from driver to the workers. So it's different directions. The accumulators are shared across different workers, so each worker can access this variable. Okay. Now we can see we have two types of shared variables supported in Spark. One is a broadcast variable. So broadcast variable is kind of from driver to the workers to guarantee that this same large data will not be sent more than once. Just they will be cached in each node. And for accumulators from another direction, it's from the workers to the driver. So in the worker, this variable will be updated and can be accessed by all the workers. And then the result is finally reflected in the driver. So that's for the accumulator. Okay. They can be used for the problems as explained here. If your problem needs such kind of shared variables, you can consider to use either broadcast variable or accumulators to do your job. Okay, so that's for the first part. Finish all the topics in the last lecture. And next is about how to write the self-contained applications. In last week's lab and also in lecture 6, what we do is based on Spark Shell. And in Spark Shell, when you use common Spark Shell, in the Spark Shell, the Spark context object is already created for you. Okay, so you can just use a Spark context object to do the interactive jobs. It's just like a command line, right? So you give some operations and it returns you some feedback. For example, if it's a transformation operation, it will tell you that, okay, given this transformation operation, so what type of RDD will be returned? So you can see some RDD with some data type. Right? So that's for transformation operation. And for action operations, and you will see the values, you will see the results. So it's different. But just like MapReduce, right? MapReduce does not have such kind of interactive command lines. They use you need to use Java to write the program and then to put the program to run in MapReduce to get the results. Spark can also do this. So how we can write the so-called self-contained applications, which means that you write a program and then submit your program to Spark. And Spark will run your program and to generate the results for you. Either the results will be stored in disks or be printed out to the standard output. So this is one example. This is standalone code for the word count written by Scala. If you have finished yesterday's lab, you should see this code. You should already see this code. Okay. The major part is just the same. We can start from this line. SC is equal to new Spark context based on some calculations. So in Spark Shell, what we do is from this line to the rest. Okay, because in Spark Shell, the Spark context object SC has already been created for you. But now in this program, you need to create this Spark context object in your program. Next, it's just word count, and finally the result will be saved in disk files. So what we need to do is that we need to understand what do these lines represent. So we need to, for the input output, we need to give the configuration for your job. So it's also like just like in MapReduce. In MapReduce, in the main function, you also need to use a configuration object and job object to configure your MapReduce jobs, right? So in Spark, it's similar. You need to have a configuration object, and then use this configuration object to initialize the Spark context object, which is used to connect your program and the cluster. Now let's explain the program line by line. So first, you need to link with Spark. you need to explicitly import the required Spark classes into your Spark program. So Spark context, and for all the other components of Spark context, also Spark configuration object, Spark conf. And based on the imported classes, then you need to create a Spark context object. And in this part, you need to give the correct configurations for your Spark context object. It will tell Spark how to access your cluster. Okay, in this example, we use a Spark configuration object. Then we set app name. So this is a name for your application word count, and set master. So this is one of the most important configuration. This is to let Spark know what is the master URL. There are different master URLs or different cluster master, different cluster managers. So Spark configuration, this is a configuration class, and set master is used to tell Spark so what kind of cluster manager Spark will use. We need to set the cluster master URL to connect to the Spark, and the parameters for this function has the following. Now, if we just debug our code, we can just use local. So this is by default, which means that it runs locally with only one worker thread. There's no parallel. Okay, so the partition is only one. There's no more partitions. So there's a default mode, and you can use this mode to debug your code. And next is local K. So it also runs locally, but with K worker nodes. Next, so these are not real distributed environments, okay, because it runs locally just on one computer. For the others that really run in a cluster, such as Spark, host, pod. So this will connect to the Spark's its own cluster URL. So Spark has its own cluster manager. And if you specify this, it means that your program will utilize the Spark's master cluster manager to do the management. So this Spark manager. And you can also use methods, which is another cluster manager. Also Apache project, or Yawn. So you can see here, Yawn is can also be used in Spark. You can specify this in the this configuration file, yawn site.xml, to connect to a Yawn cluster. So which one to use is totally up to you. Normally, we can just use Spark, uses a standalone cluster URL to do the distributed data processing. And the set master parameters can be configured in different ways. And what we have seen before is this way in source code. In source code, you tell Spark so which cluster you use. You can also specify this in Spark submit command. Okay, so I will introduce this later. So Spark submit is used to submit your code to Spark for execution. And when you submit your code, you can also specify the cluster by using this master parameter. So it's local for this master. So which means that okay, I will decide to use a local cluster, local manager for my job. And you can also use the configuration file to set values. And there are different hierarchies, different orders to decide which one we will use. So in source code, it's highest level according to this one. But if you do not do this, then it will try to check if you have specified this in Spark submit. And next, it will check if there's some configurations in this configuration file. So this for set master. Okay.
Can different machines run, the Spark mission run among different machines?
I'm sorry, what do you mean?
The Spark task
Uh-huh.
can be put it on different machines.
Yeah.
Run this one task.
Yeah.
If in this case, what should be the master origin? How to set this?
So you mean the
Like the host means the server address.
As the master URL. Yeah, yeah.
So how do you set this?
I'm not sure if I.
Must be like in the same network, or like.
So you mean if these machines must be connected by a local network or what?
Yeah, yeah.
Yeah, they should be. Otherwise, this master is not able to.
It must be in the same network.
I can't say if it is a local network, but at least you need to let the node be reachable from this master. Otherwise, the master is not able to send the data to the worker.
Can a URL be external URL, like Amazon's cloud service?
Oh, yeah, sure, definitely. So you can see host port. So host is just a URL. Yeah, and not just local host. Can also be a URL with IP address.
And why can you turn off this?
What?
Turn off this.
It's very cold?
Yeah.
It's cold? I feel very hot. I don't know. Maybe I wear too much? Don't know. Okay. Okay, it's about configurations. And if you haven't done yesterday's lab, you can try this in this week's lab. Okay. Okay. Next, I don't think I need to explain much because this is just a word count program. You have already seen this before. You raise the input file from local disk or from HDFS, and then use fetch map reduced by key to do the word count. So finally, you use this save as text file to store this data to somewhere. You can store it to local disk or store this in HDFS. It's up to you. And remember that all these are transformation operations, which means that remember that in Spark it's a lazy evaluation, right? So when only if you reach this action operation, save as text file, then all these operations will be executed. And also remember that if you save this to HDFS, also to a local file disk as well, and the number of files that are used to store the results depends on the number of partitions. So if you specify maybe 4 partitions, you will see 4 results. So 4 result files. So that's number of partitions and number of results, the relationship between them. This picture is shown to you before. So it's about the Spark component, and this is the main function. You need to create a Spark context object here, and then the Spark context in the driver function will see which cluster manager is used. It could be local threads. Local threads means that local or local K, and that run locally and not in a cluster. A cluster manager, so the different type cluster manager, Spark its own cluster manager or Mesos or Yawn, and by different cluster managers, so it will begin to allocate the resources for the workers, for the jobs. Each worker is used to execute one job in a JVM. And the results can be stored in HDFS, local file disk, or S3 in Amazon, and other storage. So this is about data flow in Spark. There's a little more details about how Spark launch a program. And I just gave you a brief introduction about the data flow in Spark. And the Spark will provide a single script called Spark Submit for you to use to submit your program to Spark. So we submit one application using Spark Submit, and we need to give some parameters for this Spark Submit. Specify our program and the master URL and our parameters. So remember that our program may take some parameters. Also, like in the third project, you need to take some parameters. And you also need to specify the parameters in the Spark Submit. And the Spark Submit, this script will launch the driver program and invoke the main method specified in your program. The driver program will contact cluster manager to ask for resources to launch executors. So here in the driver program, it will first create the Spark context object, and then according to the set master configuration to contact the cluster manager and then to ask for resources in the cluster. Okay, so next, according to the number of partitions, so the driver will push the relevant data and closures to the executors for execution. And so the executors will be launched by the managers. And okay, so then next, the driver process will run through the user application. So based on the RDD action, transformation actions, action operations in the program to do the relevant tasks. And then after the tasks are run on each executor and after all of them have finished the jobs, the results will be saved according to your program as well, saved in HDFS or saved in local file disks. So if the driver's main method exists or it calls Spark context stop, it will terminate the executors and release the resources from the cluster manager. So this is a whole data flow in Spark. So you submit your program to Spark, and Spark will, according to the configurations of your program, and also according to the parameters in Spark submit, to contact the relevant cluster manager and ask for the resources, and then invoke the executors to run the parallel jobs according to the RDD partitions, and then the results will be saved. So each partition will result in one file, one result file. Okay, so in Spark, we have different ways to package your code and dependencies. You can use Maven, but in our course, we choose SBT, which is normally used for scale-up projects. So Maven is mainly used for Java application. For scale applications, SBT is a more suitable tool for you to use. It's like Maven actually. You need to give a configuration file, and then based on this configuration file, this build file, so SBT will build your project according to the configurations in this build file. So for example, here, we gave a name for this project, gave a version. So this version is our own application's version. And Scala version must be consistent with the Scala you used in your computer. And this is the most important one because this specifies some dependent libraries. You must specify what libraries my program depends on. So otherwise, your program cannot be compiled successfully. So it's a Spark call and a Spark and Spark call with version 2.3.0. It's the most recent version. We also use this version in the labs. And we need to list all the dependent libraries in this file, also including the third-party libraries. So these are Spark libraries, but if you use some third-party libraries, you also need to list these libraries in this file. And then you use SBT to do the completion. The jar file will be generated. So this is a name based on what you gave to this program, this project, simple project. And this is a version of Scala, and this is a version of your program. And a jar file will be created. So what we need to do is next is to submit this jar file to Spark, just like you in MapReduce, you use the jar file to run the jar file in MapReduce. Here, after you create this jar file, you need to use Spark submit to submit your program. And we have seen this before, master parameter to indicate the cluster manager to connect to. So according to this, Spark will contact the relevant cluster managers. And class, so this is the main class of the application, also similar to MapReduce, right? In MapReduce, you also need to give the main class. This is the entrance of your program. So otherwise, a Spark or MapReduce, they will not be able to know how to enter your program, how to start your program. And name, so this is a human readable name for your application. And this is used for debugging because you may run many applications in Spark. So with this specified name, and you can check the status of your relevant applications. You can also see this in Spark's web UI. And executive memory is this used to allocate the message amount of memory for each executors. So this is in bytes, such as 512 megabytes or 15 gigabytes. But this depends on your cluster, right? You need to know how much memory is available in your cluster. Then you can compute good value for this executive memory. And driver memory is used for the driver process, also in bytes as well. But normally we care much more for this one because the executive memory is used for doing the jobs. Okay. This is one example about how to submit your program. So we Spark submit to this master URL. So this, according to this, we know that this is a Spark standalone class manager, its own class manager. And this is a URL and this is a port. It tells where you can find the class manager. And then class, this is the main class of your application. You must give the name of your main class. Next is about executive memory. So each executor can have 2 gigabytes memory to run this job. And this is your jar file. Your jar file is specified here. Next is parameters. So 1, 2, 3. So here you have 3 parameters. So they will be used in your program, in your own program. Okay. After you do this Spark submit, then your application will be run in Spark. So just need to wait for the results. You may see some logs. Okay, so that's all about the Spark core part. As a slide for Spark programming, the most challenge is that you are not familiar with transformation and action operations, and you are also not very familiar with the scalar. So my suggestion is that you just need to do more practice to be more familiar with Spark programming. I provided many practice in this week's lab and also next week's lab. There are some problems for you to practice. I will also release the solutions 1 week later. But before that, I suggest that you try your best to solve the problems because some problems are actually from previous year's exams. So you can see in the exam if you are able to solve such problems in a limited time period, right? So in this year, the second problem is about Spark, and you also need to write a Spark program for the given problem. And I have to say, actually, that problem is not very easy, so you need to be careful, okay? Because the time is very limited, only 2 hours for the exam. There are 5 questions, so it's a little bit challenging. Okay, anyway, so let's first do a practice. It's one problem. So let's see what we can do in Spark, how we can utilize Spark transformation and action operations to do some analytic jobs. The problem is like this. So given you a pair RDD, as a pair RDDs is a string and integer. As a data type, key is a string. Integer is, values are integers. And we want to compute the average value for each key. So for example, we have 5 keyword pairs, and there are only 3 keys. And for panda, it's 0, 1, and pink is 3.5, and for parrot, it's just 1 keyword, it's 3. Okay, so 0 plus 1 divided by 2, and 3 plus 3 divided by 3 plus 4 divided by 2, and it's 3 divided by 1. So that's the result, the input and output, and what kind of operations you can use to solve this problem. So in MapReduce, it will be very easy, right? So you can think about MapReduce. In Mapper, it's just an average, right? So we have learned this before. It's just how to compute average. Now let's look at how to compute average in Spark. I can give you one. Let's have a short break first, and then you can also think about the solution for this problem. Okay.
practice.
Uh-huh.
For example, if I am working in a company that uses Spark and I want to save the result in a database,
In a database.
all right?
Uh-huh.
Yes, a relational one, right?
Database, yeah.
But this database already have the whole schemas.
All the schema. Yeah,
There's
yeah.
a table, and I have to insert new lines in this table. Is there a way that I can replicate this schema to the workers so the main executor, the code, so it can insert in this table?
So we want to store the result directly to the relational database
Yeah,
with
but
existing schemas.
there's already a table there.
Already table there.
Yeah.
I just want to store this result to the table.
Yeah. So imagine that I am working a project. In this project, I already have a class that represents the table.
Okay. I'm not quite sure if a Spark can do this directly because so what I know is that Spark provides some APIs for you to store the result to such as HBase, but it's not relational database. It's it's like Google's big table, so it's non-SQL database or
It doesn't have connection with relational database.
should have. Let me check. The slides have. I'll check the slides.
Week 6, we'll talk about that.
Yeah, I think there's my figure. Yeah, RDBMS. Yeah. Okay. So I think you can do this, but I need to check the relevant instructions. Yeah, I have done this before. I have to confess that I never store the results from Spark to RDBMS directly. But it seems that you can do that. But how to do that? You can also go to the Spark website to see more details. It can also help you to check if there are some menus.
All right.
Okay.
And another thing, between we can use Spark with Java, Scala, and Python, right?
Yeah, Java.
Amongst these three, Scala is the easiest one to work with, like it's more productive.
So, yeah, Scala, we use Scala because we can use Spark Shell. In Spark Shell, you can only use Scala to do interactive jobs. But if you just want to write the standalone applications, you can use Java, use Python, it's quite okay. It's
But
okay.
is it harder to use, for example, in Python?
No, it's very easy. Python is also very easy, yeah.
Yeah.
It's not like in MapReduce. In MapReduce, using Python is still very different from using Java. But in Spark, using Python is, I think it's almost the same level as using Scala.
Yeah, because I saw the code in Python.
Yeah,
It
give
very,
you
very similar.
very similar with Scala. Yeah. So you can use Python for Spark programming. It's okay. It's totally
Okay.
fine. Yeah.
And tell one more question. When I have my cluster manager and I submit file to him, all right? It stays there, or does it only run when I submit and that's it? He forgets this file, the jar.
The jar.
Yeah.
So you compile. You have to remember MapReduce, right?
No, Spark.
I know. I mean, it's similar. Yeah. So you
okay.
compile your jar and you submit your jar to Spark, and then the jar will be received by the cluster, and then the driver will run your jar file.
Okay.
It's like this.
All right.
Yeah.
And last question.
Okay, no problem.
If I am working, I have a big platform, for example, and this platform needs to run many different processes in Spark. How does the cluster manager deal with that?
There's only one cluster manager. I didn't understand.
For example, I have another platform. This platform, time asks the Spark to run some stuff to him, right? Could be some report or update some data. So if the cluster manager receives more than one request, he serializes. He does one and then does other, right?
Oh, you mean your cluster will receive many requests?
Yeah.
Yeah. So
How the cluster manages that? Because it does not do more than one request at a time, right? Just one per time.
no. It's also it depends on the cluster, your cluster computation power. So if there are some available nodes that you can use, then that request will be processed. So this node can run some executor to run the Spark program. Yeah.
Okay.
Yeah. So we don't need to know details about this. So because there is a cluster manager, so the cluster manager will allocate and manage the resources in the cluster to do the job application.
Okay.
Yeah.
Right. Remember the other stuff within a worker. He's doing the filter. He filters and then count and do this kind of stuff. He creates a new RDD every time, right?
Yeah, that's true.
So every time that he creates a new one, within him, he forgets the other RDD?
Yeah, the old RDD will be discarded if you do not use persist or cache.
Okay.
Only cached data will be stored in memory, otherwise it will be discarded. Only the new RDD will store.
All right. And if it is too much to him and I didn't set to run to write in disk, what he's going to do?
You mean you persist too much data in memory, or what?
For the workers, the RDD is too big.
It's too big.
Became too big.
But some of the data will be put in memory. Sorry, to disk. Or according to Spark, yeah, some if your RDD is too large to be loaded into memory, and some will be stored in disk, not just on
right.
Yeah, because the memory is not enough to cope all the data.
Even though that I didn't set to do that memory and disk.
That's for persistence, not for data storage. You mean the RDD is too big, not the persistent RDD is too big.
Yeah,
Yeah.
the RDD became too big, for example, within a work.
If the RDD is too big, so yeah, some of the data will be stored in disk, not just in memory.
Okay.
But if it is a persistent RDD, and if you specify that must be kept in memory, and then the data that cannot be held into memory will just be discarded, will not be stored in disk. They will just be re-executed time by time.
Right.
Yeah, so it's different.
Okay. And Professor, if I have two different data sources and I need to join two different data and get this data and pass to the worker, for a worker to do some stuff. So just like a join, but it's two different
data
sources.
sources.
Yeah,
Right.
it's possible to do that in Spark in one code, right?
What do you mean by the data source? If you just two input files, then that is totally fine.
Yeah.
But-
yeah.
But remember that what is the input? So the
For example, temperature is one file and sales is another.
yeah, if it's just two files, it's okay. You can just need to read the two files which means that you just load two files as two RDDs in the memory. Then you do the joins for the two RDDs. So that's totally fine. That's no problem.
Okay,
Yeah.
but who does that is a worker, so the partition. Okay.
It's just about RDD operations. It means you just have one RDD for this file, another RDD for that file. So
Yeah,
then
but
you
we need to join that before, right? Before giving to the worker. Then we partitionate that.
But you can use RDD operations to do the relevant jobs, right?
Yeah. Okay. Okay. Thanks.
我想问明天放假上来不？
明天是 public holiday 吧？
还是在这个
如果是 public holiday 的话，应该
4月25
应该就是不用上了。
上那还顺延了，还是怎么？我明天来过。
如果是 public holiday 一般是这样，一般 public holiday 不上课。
对，我那我什么时候去新思学？
哦，你是说那个来不来是吧？我不确定说周四或周五会不会有，不根据现在的情况，似乎明天来都可以，因为现在我来的人来少，明天来都可以。现在这个问题。Oh, sorry. I showed the results. Okay, so let's continue. So this is about how to compute average in Spark. We have seen this before in MapReduce. Now let's look at how to do this in Spark. What we need to do is that, so definitely first we need to to group the keys for the values for the same key, right? So if we get this group of values, then we can compute average for them. But there are also some other ways, but anyway, this is the most easy way to do this. So we can use group by keys. That's a different solution. But after you do the group by keys, so what you get is the key and a list of values. And then for the list of values, you just do a sum and then count the number of values, then do an array, do a division, so you can get results. But just like in MapReduce, it's not. It's hard to do parallel jobs. So what we do is like this. This is similar to what you did in MapReduce. Actually, you convert the values to the key to a pair. One is a value itself, another is for the count. Okay, and so this can be performed by map values. So remember, we can do map values. And next, we can just do reduce by key. The previous solution, I said, is that you can do group by key, group by key, right? But group by key, the problem is that what we care about is only the average. We only need to know the sum and the count, but we don't need to know the set of the values. But group by key will give you all the values stored in memory. So which means that you waste a lot of memory space to do this job. So that's why this is a better solution, because by doing this, you get the value, the count, and according to reduce by key, you just do a sum. So both the two components in this pair will be summed together. And as a result, for each key, we will get a sum and a count. So in group by key, we'll get a group of values, right? But here, we just get the sum and the count. They are the only data we care about. So now, next, we just need to do a division. Use this sum divided by this count. We can get the results. Then this can be performed by map values again. So this is operations we need to use. And detailed code is like this. So first, we use map values. For each value, we transform it to the value itself and count 1. And then we do a reduce by key. So this is sum for both components. So values are summed together. The counts are summed together as well. So next we will receive something like this. We get something like this, right? So next we do another map values. We use _1. So this is used to denote the first component of this parameter x, and to double to guarantee the precision, and divided by the second parameter, which is the count, underscore. So _1, _2 is used to point out, to represent the components in this parameter x. And so finally, we will get the result like this. So let's look at code. It's very like MapReduce, right? In MapReduce, we also do the same thing. We map in Mapper. We do the map like this. We map values, right? And then maybe we have some combiners just in our first project. And in the reducer, we also do the sum, and we sum the values, we sum the counts, and then we do a division. So this is a map phase in Mapper. In MapReduce, this part is a reduce phase in MapReduce, right? But remember that how many code you need to write in MapReduce? It's a lot. But in Java, in Spark here, just 3 lines is already enough. And also the efficiency is also better because it is in memory. All the data is in memory. But in MapReduce, you need to load data from disk to memory. And if you are later, we will do some labs on AWS. So if you are interested, you can do this. You can do the same job by using MapReduce and then by using Spark again to compare the differences, to compare how much time it will cost in MapReduce and in Spark. So this is final solution for this problem. Is there any questions? No. In the third project, for the first one, it's much more complicated than this, and the second one is it uses GraphX because you are not familiar with GraphX, so maybe you will also meet some problems. So after this, the third project is also a little bit tricky, so you need to spend some time for learning Scala and learning Spark programming, and you can do more practice like this. In the labs, we have several problems, so try to solve them on your own. So if you are able to give some solutions like this, then you should be able to finish the third project and also be able to do the exam questions very well. Okay, so if we have time, we can see more problems, but I will skip this one because of time limit. Okay, so this is Spark Web Console, and this is a Spark Web UI. You can use this URL to see the status of each job. So for example, here we can see there are jobs tab, stages tab, storage tab, environment executors. For all the tabs, you can click and see the status of how your job is performed in the Spark cluster. Okay, this is a comparison between Spark and MapReduce. Because data is in memory, so we can see that the result is the gap is very, very huge, right? For k-means for this clustering task, Hadoop may take about 120 seconds, but for Spark, it only takes 4 seconds. You can see it's about 30 times faster than MapReduce. And in this logistic regression, Spark is about 80 times faster than MapReduce. So this figure is about at least 4 or 5 years ago. So I believe that the performance should be much, much better nowadays. So that's why in graph algorithms or in machine learning algorithms, especially when the data is not that large, so your cluster memory is able to hold all the data. So Spark is always the first option for you to use. MapReduce is not suitable for graph and for machine learning algorithms. Okay, and okay, so next we move to the topic about Spark GraphX, which is about the second problem in our project. When we learn the graph data processing, we mainly use MapReduce, right? At last, we briefly introduced Prego. So we can see the difference between MapReduce and Prego. So MapReduce is not designed for graph data processing. So that's why you need to waste some computation on unnecessary nodes, and also there's some other costs on the I/O, on the startup, on storage. And Prego is a computation model for graph data processing. And GraphX, Spark GraphX, so why we still need to use GraphX? The motivation of GraphX is different from MapReduce and Prego because it aims to provide both views, a table view and a graph view for the same type of data. So in MapReduce, it's only a table view. In Prego, it's only a graph view. But in GraphX, you can view the same piece of data as both tables or graphs. And as a result, you can use both table operators and also graph operators to do your jobs. And at high level, GraphX extends the Spark RDD. It's also based on RDD by introducing a new graph abstraction. So it is a directed multi-graph with properties attached to each vertex and edge. So this is a graph. And in this graph, there are vertices and edges. And each vertex and each edge can have some properties. And so this is kind of a property graph in GraphX. So it's a data model of GraphX. In order to support graph computation, and GraphX exposes a set of the graph operators, such as subgraph, and so you can take subgraph from the whole graph easily, and as well as an optimized variant of the Prego API. So Prego is also supported in Spark GraphX, but it's a little bit different with original Prego because of the optimization objectives. So GraphX has a little bit, just slight difference. And GraphX includes a growing collection of graph algorithms and builders to simplify graph analytic tasks. So which means that more and more operators have been integrated in GraphX in order to do different types of jobs. So there exists some graph processing platforms. For example, the Giraffe and GraphLab, and Prego is also one of them. And just because graph data is widely used, and it is more and more important to analyze graph data. But these systems can efficiently execute sophisticated graph algorithms orders of magnitude faster than the more general data parallel systems, such as MapReduce. And because they have some kind of specialized APIs to simplify the graph programming. For example, so without GraphX, you can also use Spark to represent a graph. Remember that the graph can be represented by a adjacent list, right? Or just a pair of nodes. So a list of a pair of nodes can also be used to represent a graph. So you can, as a result, you can use a Spark call or MapReduce to do the analytics. But it's kind of a table view, right? So there are rows, and then you based on the rows to generate the results. But for the graph-based systems such as Prego, Giraffe, GraphLab, so they have some specialized APIs to do the graph programming instead of so they provide a graph view for data instead of the table view. So it's a difference between the two types, and it is because they aim for graph data processing, they are more efficient than the general big data processing platforms. But the problem is that the specialized system may also miss some points, miss because bigger picture. So it is often, this is the reason is that it's often desirable to be able to move between the table and graph views for the same physical data, and to leverage the properties of both table view and graph view to express as a computation. And because for some problems, and the table operators is more efficient and easily to use, and for some problems, the graph operators would be more useful. So that's why Spark began to develop GraphX, because it tried to aim to provide both views, both table view and graph view, and both table operators and graph operators for the same physical data. So this is one example. Assume that we have the raw wiki web pages. It's based on HTML, right? So we can begin to analyze HTML to big table, the text table, the title and the body, page body. And next, we can have different types of graphs, such as hyperlinks. In Wikipedia, so it may point to, may have inside the page, the content from another page. So we can create a hyperlink graph, a directed graph. And so based on this hyperlink graph, we can do some page rank to compute the important pages. And we can also have the term dot graph. It's a bipart graph, which means that this is the terms and this is the pages. And as a result, we can do some text mining problems, and such as natural language processing. Or so this example uses a topic model. We use LDA to analyze the topics for the documents, and then we can also compute the word topics. So there's a distribution of topics. So each word has some probability to belong to some topics. So this is about the RDA model. And so this is about the graph view, right? And we can also use table to analyze the data. So for example, here is a discussion table. We have the user and user descriptions. And based on the editing history, we can create an iterated graph. And this is a user connection graph. So for different users, we can create an edge if there are some connections. So based on this user graph, we can do community detection. And then user community, we have a table, right? So we can also, based on this table, we can also do some topic analysis. So in the whole picture, we can see that sometimes we need the graph. We need the graph presentation. representation of the data. Sometimes we need a table, representation of the data. So which means that for both the general big data problems, big data processing systems, or the specialized graph processing systems, they both miss some parts, right? So GraphX, the motivation of GraphX is to combine them, to unify the graph parallel and data parallel computation in one system with a single composable API. So both table operators and graph operators are provided for you to use to analyze the data. So when you want to treat the data as tables, you use table operators. When you want to treat your data as graphs, you use graph operators to process the data. So this is one example. So you can process your raw data and create a graph, and you can get some subgraphs for processing, and based on a graph, you can compute PageRank. And next, you can, according to the PageRank results, you can create different tables. There's a ranking, top users, top pages, and based on the table, so you can do some other tasks. You can also repeat. You can use the table to create a new graph for the processing. And in this whole procedure, just both type of operators will be very useful. And tables and graphs are composable views of the same physical data in Spark GraphX. And this is a unified representation. So the same data, and it depends on what kind of problems you want to do. If it's a graph relevant problem, so you use graph view for the data. If it's it's a general purpose, so you use table view for the data. And each view has its own operators. And so let's look at one example. So we write a graph as a table. This is a property graph, and it's directed graph. And each node and each edge has some labels or properties. So the node labels are the names. So Franklin, so actually they are the developer of the Spark project. So this is a leading professor. And there are some relationships on the edge. For example, this professor is an advisor of this student, and this colleague with this professor. So given this graph, we can create two tables. One is a vertex table. So vertex table is the node ID and the property type, the attributes. And for the edge table, we have the source ID, the destination ID, and the label on the edge, right? So now this is different views for the same data. This is a graph view, and this is a table view, right? For table operators, actually we have already seen them. So they are just the RDD operators, transformation operators, and action operators. So we call them table operators because the data are stored in RDD just like a table. Actually, not a real table, but it's just lines of records, right? So just like a table. And different type of operations can be utilized to do the operations. For graph operators, this is a little bit different. These graph operators designed for you to use to do the specialized graph operations. So for example, you can, these are some information about graph, the number of edges, number of vertices, and the degree, up degrees, and here are the views of the graph as collections. So vertices is all the vertices, and edges is used to store all edges, and triplets is to store the edge triplet. So I will explain what this is in the later slide. And next is about how to transform the vertex and edge attributes, because sometimes you need to do some computations based on the attributes in the graph, the attributes on both the vertices and the edges. So you can do map vertices, map edges, and map vertices will take the existing vertex and attributes as input, and based on the function you gave to this map function, and will do some kind of transformation for the attributes. So these functions will not affect the graph structure. So the graph structure will not be changed. They only change the attributes of the graphs. Okay. So if you want to do the attributes modification, you can also first modify the attributes and then create a new graph. But that is not efficient. It's because it cannot utilize graph X optimizations. So that's why when you want to modify some attributes, it is always suggested to use these map vertices and map edges operations to do the mapping. So later we will use graph X to solve the single source shortest path problem. So in that problem, we also need to utilize this map vertices operation. So we will see the example later. And these are the transformations. So this is a map triplet to change the attribute of the triplet. So a triplet, it's called triplet because it involves 3 components: one source node, one target node, and one edge. So that's called a triplet. And later you can have some other operations to modify the graph structure. So they will not change the graph structure. They are used to change the attributes. So these are used to change the graph structure, such as reverse. So remember that in MapReduce chapters, you are given a question on how to do the edge direction reverse, right? If you still remember, so what you need to use, secondary sort, right? In that problem, you need to reverse the directions of the edges. You need to write some code to do that, and also complicated code because you need to do secondary sort. But here, reverse, it's just one function. It will reverse the directions of the graph, or the given graph. So very easy. And subgraph is to take the subgraph according to some functions. So which means that if some node and edges satisfy this given Boolean function, then it will be extracted and other nodes will be thrown away in the graph. Then you generate a subgraph. It returns a graph to you, which is a subgraph of the current graph. And next is group edges. It's used to group the random edges. Again, it depends on merge function. You need to tell the graph how to merge some edges. Then a new graph will be returned to you. There are also some other operators. You can go to the Spark Graph X homepage to check more details about these operators. So you can see that these are specialized operators for graphs, right? So normally they cannot be used for the general purpose data processing. And the data type in graph X is called the property graph because it is a graph with properties. And it is a directed graph, so it means edges have directions. And each vertex and edge are attached with some properties or attributes. And so this is also a multi-graph because a simple graph is that between each pair of nodes, there's only one edge. Okay, but the multi-graph means that there are multiple parallel edges between 2 nodes. So this because each edge may represent a different relationship. So in graph X, they use this directed multi-graph with properties as a data type to represent the graphs. And it is parameterized over the vertex, VD, and edge, ED types. So these are the types of the objects associated with each vertex and edge respectively. So you need to give the vertex type and also the edge type. And each vertex is keyed by a unique 64-bit long identifier. It is already large enough to represent the graphs. Normally, it's not possible to exceed this value. It's a very, very large value. I never see a graph with so many nodes. And edges have corresponding source and destination vertex identifiers. So given source node and destination node, so this edge can be identified uniquely. And logically, the property graph corresponds to a pair of typed collections encoding the properties for each vertex and edge. So the graph data types like this. So this is graph class. And you need to give the data type for vertex and for edges. So for vertices, it is a vertex RDD. This is the type for this RDD. And for edges, this is edge RD, and also data type for the edges. Okay. And this is a graph we have seen before. So we can use graph X to represent this property graph. And in order to create a graph for representing this property graph in Spark, we need to do the following. So this is a graph X example. So what we need to do, assume that it is a standalone project. And so you need to import the relevant Spark classes first. This is graph X, so you need to import graph X relevant classes. And you also need to use some RDDs because some operations requires a RDD class. So in this graph, we know that we can see that we have 4 nodes with some properties, right? So we first have a vertex array. We use an array to store the nodes. 3L used to denote the long data type with identifier 3. And it is a name and a row, name, row, name, row. We have 4 nodes, so this is a vertex array. And for edge array, we need to give the source node, the destination node, and the relationship between the 2 nodes, such as its collaborator, a colleague, advisor, and so this edge array. And given the vertex array and edge array, now we are able to construct this property graph. So what we need to do, we also need to create this Spark context object first. And if after you create this Spark context object, then we need to use RDD to parallelize the vertex array. So originally it is just an array, it's not RDD. We need to parallelize the 2 arrays to RDDs. So this is parallelize the vertex array, parallelize the edge array. Now we get 2 RDDs. One is used to store the vertices and another is used to store the edges. Okay. And we can define a default user just in case there's some relationship with a missing user. So now, given the user RDD and the edge RDD relationships, and also with a default user, now we can create this graph. So in this graph object, it actually represents this graph, and it contains all the required information in this graph. Okay, and it's users RDD, nodes RDD, vertices RDD, and edges RDD. And so for the edges, each edge has a source and destination node, and also have a attribute member to store the edge property. So you can see like this. Okay, this one?
No, before. Yeah, this way. In the place of advisor, can I put a function?
Advisor?
Yeah, in the edge array.
Here?
Yeah, the second line below.
So what's it?
So instead of putting string, can I put a function?
A function here?
Yeah.
No, it's an attribute. You can't do a function here.
Must be string or integer, something like that.
Yeah, it's used to define attributes for this edge. Okay, it should be a value. And so this is about how to construct this property graph. And given you this graph, you can also deconstruct the property graph, which means that you can get the vertex arrays and the edge arrays. So here, this is a graph. Assume that given the graph, you have the vertices and edges. And now how to get the users and get the vertices and edges according to some conditions. So here we give you 2 examples. For example, if we count all the users which are postdocs, so postdocs are the attributes on the vertices, right? So it means that we need to deconstruct the property graph according to the vertices and do some filter. And the solution is that we first get the vertices. So graph.vertices will get vertices RDD. Remember, this is RDD. And filter. And case is to check if the format is like this. If it is a format ID and name and the row or the position, then we will check if the position is postdoc. If so, then it satisfies this filter condition, right? So it's a filter. And then we do a count. It will return the result for us. How many postdocs in this project in the graph? This is for to get vertices, and this is to count all the edges where the source node ID is larger than the destination node ID. So we add filter, and each in the edges RDD. So each edge has several attributes. One is a source ID, and another is a destination ID. Sorry. So you can use E to get the source ID and destination ID and to compare if the source ID is larger than destination ID. If so, it satisfies this filter condition, and we finally do the count for all such edges. And we can see that we can use vertices to get the vertices RDD and edges to get edges RDD. And the vertices return the data type like this. It's vertex RDD, and the string is for the attributes name, and the string is for the position here, postdoc. And the edges return the edge RDD, and this string is also for the attributes, the type of the attributes. So you can see why it can't be a function, because you must give a data type for the attributes. Okay, right, sorry.
So what's the data type of the ID?
Here ID as a node ID. So remember that for each vertex, there is a 64-bit long variable to represent to identify the node directly. So ID is just a node ID, a long variable. Yeah, long variable. Okay, so the case is this direction statement is used to check the format to satisfy this ID name and position. Also match the data type. So this is used to do these things. So edges filter, and we check case to check if it is an edge. And if it is an edge with source, destination, and properties, then we get source and destination for the comparison. So it's different representations for the filter function. Okay, it's the deconstruct property graph. So the basic operations here in this slide is still based on the RDD operations, right? Filter and count, that's still table views. Now let's look at the graph views, how we can use graph views to do some things. In many cases, especially in the graph learning problems, we want to extract the vertex and edge RDD views of a graph. And the graph class contains members. The vertices and edges are two RDDs to access the vertices and edges of the graph. So that's why we can, as a result, we can use them to get the two RDs and as a graph views. And then next, based on the two RDDs, also based on the graph object itself, we can use the graph operators. So the graph views mainly means that we want to use the graph operators to do some operations. And so this is still similar to the previous slides example, and this is a filter. We want to check the names of the user who are professors. So we want to list all the professors actually. So what we can do is that we first get the vertices RDD, and then we filter. We only get the data whose position is professor, right? And next, we get all the professors. So according to this filter statement. So for all the professors, we collect. So remember that collect is action operation. And we collect, and then for each, we print their name. So who is a professor? According to this name attribute, we can get all the professors' name. So this about how we can use the graph, this graph class to do some things. Okay, so next is the triplet view. So remember that in graph operators, we have some triplet and triplet relevant operations. A triplet is like this, and it's logically joins the vertex and edge properties and yielding RDD called edge triplet. And it is more easily to understand what a triplet is from this graph. So remember that we have vertices, right? And we have the edges to connect the vertices. And if we view them separately, so we have vertices set, we have edges set. But here we have a triplet view, which means that we join them together and also with the properties. So now the triplet is like vertices, source vertices, and the edge attributes, the relationships between the vertices, and the destination vertices. Right? So that's why it's called triplet 1, 2, 3, right? And vertices with properties, edge properties, and destination vertices with properties. And it can be expressed by this secure expression. So we select, assume it's from table. We select source ID, destination ID, source attribute, and destination attribute, and the edge attribute. And the select condition is we select from the edges as E, left join vertices as source and vertices as destination. So A, B, so this is a source, this is destination, and in the middle it is edge. And we do a join according to this condition. So the source ID of the edge is equal to the node's ID, and the destination ID is equal to the destination ID. Then, so finally, it's that join as a triplet. So we can also view this as a table, triplet table. Then just 3 components: destination, source nodes with properties, and the edge properties and destination nodes with properties. So this triplet view. And the result is stored in an edge triplet class. So this triple edge class contains the edge class, but adding the source attribute and destination attribute members. Okay. Previously, edge class only contains source ID, destination ID, and edge attribute, but now it has source attribute, destination attribute, together with the source ID, destination ID, and edge attribute. And now we can use a triplet view or graph to render a collection of strings describing relationships between the users. So for example, let's look at this code. We have a graph, right? In this graph, this is attribute types for the vertices, string, a pair of string. And the attribute type for the edges, also string. Now we use the triplet view to create an RDD of the facts. So there's a facts, it's RDD. And the objective is to check what kind of attribute of another type of what. So this is a source attribute. And we have the triplet, right? So then we can use the triplets and map to obtain the facts RDD. So triplet to triplet source underscore 1 is name, right? The first component is a name. Name is this is a triplet attribute. Remember, it's a colleague or advisor, right? That's a relationship. Of and triplet destination attribute underscore 1 is also the name of the data node of another person, right? So now we can generate all the relationships, and next we print the result out. So someone is the kind of relationship of some other person. So that's our final result. Okay. So that's edge triplet. They are introduced because later in the shortest path problem, we need to use them to do something. Okay, so remember this; they are very useful. Okay, now we move to the Prego operator, which will be useful for your second problem in the third project. this is a review of what we have learned before when we learned graph data processing. So Pregel is based on this BSP model called bulk synchronous parallel message passing model, and it's based on the super steps. The processing is just a series of super steps. So it is a vertex-centric computation model. And it just like it thinks from the view of a vertex. It defines what a vertex will do. So the vertex will receive some messages. And on my vertex, after I receive some messages, I will do something, right? And then after I do something, I need to send the message out to my neighbors. So you need to define the vertex behaviors. And so that's all the computations. So all the computations are defined over the vertices. And now, so all the vertices will do the computation in parallel, and each vertex V may, as a side, receive some messages, and then perform some computation, and then send message out. So that's for in one round of super step. And in next round super step, so the messages will be sent out to different nodes. And then from next round, this will be repeated again. The nodes receive some new messages and do some computation and send new messages to the neighbors. And it's called the vertex-centric message passing computation model. So that's Pregel. And in Spark, it has a Pregel operator in GraphX. And also, these operations receive messages, perform computation, and sending messages are all supported in GraphX in this Pregel operator. So which means that what you need to do is to tell GraphX for your problem when a node, how the node will receive the messages, and how the node will do the computation, and how the node will send out the messages to the neighbors. So that's what you need to do. And then next, you just need to call the Pregel operator to run to do the execution and to get the result. Okay, and this is a definition of the Pregel operator. So it's a little bit complicated. I'll try to explain a little bit. And because without explanation, it's not possible for you to use the Pregel operator. And this is a source code in Spark actually. So it defines the Pregel operator. And this is a data type, and it has I need to take two lists of parameters. So this is the first list called initial message. Initially, before the jobs are run, so each node will receive some initial message, and you need to define this. And next is a max iteration. So because this is iterative job, right? Just like short pass, it's iterations. But just in case some problems, some bugs in your code, then you can set the maximum iterations. So when your program exceeds this iteration number, it must represent that there's some problems in your code. So the Spark will terminate your program just in case it runs in forever. And there by default is a max value because normally we don't need this. And next is the active direction. It tells Pregel how to send the messages. So by default, it's just based on the outgoing neighbors. So edge direction dot out, but which means that you can also based on the in directions, right? So edge direction in. Talking about here, I just remember that for the second project. And the second project is previously the single target, a single source short pass is based on outgoing neighbors, right? And what I expect you to do is to now to do the computation based on incoming neighbors, right? But someone gave me a very smart solution. It reversed the graph first, then still based on the outgoing neighbors. That's very interesting. This is beyond my expectation. But I think the result should be correct, so I will check later. It's very interesting. So it means that giving you the single source shortest path problem, right? And then you just need to change this from out to in, then you get a single target, the shortest path solution, right? So it's very interesting. Okay, so that's our first set of parameters. We also have another set of parameters. So you can observe that actually there are two brackets, right? What does the two brackets represent? It's a little bit different from what we have learned before. When we learn Java, we learn C++, Python, we never see this, right? So it's a feature of the Scala, so I've introduced in the next slide. And anyway, it's just another list of parameters. First, it's called the vertex program. And this vertex program is a user-defined function. So you need to define this vertex program. What does it do? It tells the Spark GraphX how to receive the function, the messages. So it's about receiving messages. Remember, in Prego, you need to define receive messages, do computation, and send out messages, right? So this is for the first one, receiving messages. And send messages is the second parameter. You also need to give another function called send messages. So you need to tell GraphX how my node will send out the messages to And by default, it's based on the edge direction, based on the outgoing neighbors. The last one is called message merge. And actually, this is about how to do the computations on a node. It's called merge messages. You need to, you receive many messages, right? And then you need to do something for these messages, a kind of merge messages. And these are the types of the functions. So, given this definition of the Prego operator, so you need to know that what you need to do. First, you need to give the initial messages for the Prego operator. Taking the shortest path problem as an example. Initially, for the source node, the distance is 0, and for all the other nodes, the distance is infinity, right? So that's kind of the initial message. So in the shortest path problem, you just need to give an initial message like that. So that's the initial message. You pass that initial message function to this Prego. And, oh, sorry, that's not a function. And next, you need to remember that these three functions are most important ones, are the key parts of your Prego programming. Okay, because in Prego, the most basic three operations are receiving messages, do computations, and sending out messages. So here you need to define how to receive messages, what a node will do when receive a message, and what a node will process all the received messages, and what messages will be sent out by a node. So they are defined in these three functions. And this is returned value. This type of the return value of Prego is return graph with type vertex data type and edges data type. So in between it's a function body of Prego, so I don't want to show the details. You can go to the Spark GraphX homepage to see more details about this Prego operator definition. Next slide, there are two brackets after function definition, right? So in Scala, it's called Scala carry. Idea is that the methods, each method, a function, can define multiple parameter lists. And when a method, for example, here we have two lists of parameters. One is n, another is x. So the function is very easy. It's x mod n is to check if x mod n is equal to 0. And when you use this function mod n, the Scala will check if you have provided enough parameters. So if you provide enough parameters, then it's fine. You just return, so for example here, it returns true or false, right? This is a Boolean function. But if you do not provide enough parameters, this function is called with a fewer number of parameter lists, then this will yield a function taking the missing parameter list as an argument. Okay. So for example here, we have a list. And if you do nums, this list filter mod n 2. So we can see that actually 2 is only for n. okay? But X is missing, right? So which means that now your code with fewer number of parameter lists. It's only one parameter list, but X is missing. So as a result, X will be treated as a parameter for this function. And where X is obtained is from the nums, because it's the filter function. So each member in this list will be sent to this mod n as X. So if you check the results, actually you can view this, actually we can view like this. Nums filter mod n2 is equal to nums filter x to mod 2x. So x is this parameter here. And now, because x is treated as an argument, as a parameter, so the result will be all the numbers mod n with value 0 will be reserved, right? Or 2, 4, 6, 8 will be reserved, but 1, 3, 5, 7 will be discarded. And now let's go back here. We have two lists of parameters. So which means that you can just provide this parameter when call this Prego operator. But where to find these definitions? They are treated as parameters, right? So just like here, they're treated as parameters. The reason is because just like here, there may be multiple input in a function call. So then the Prego operator will be used for all the multiple input to do the processing, to do different types of processings. And they will define different receiving messages functions, sending messages functions, and merging messages functions. Okay. Okay, so this is called scalar currying. That's a little bit different from what we have learned before. So, okay, before we move to how to use Spark Prego operator to solve short spots problem, let's have a short break first. Okay.
Yes.
因为它这个，它应该，我觉得 underscore 是应该加到这儿 as a capital size。
是触屏的，我还真不知道。
这个 underscore 是不是应该加到这个地方，就是作为一个 parameter，作为一个 input。
点杠是吧？啊，我想想啊。
因为这就省略了说就是 for each element x， 然后就省略了这个 method。因为不然的话，不知道就是说 each element 是这个 parameter 是怎样 map 到这个。
filter 是可以直接 take 一个 function 作为 parameter， 这我得查。
它是默认那个，它是默认说这个 function 是 apply to， 它会自动 pass 这个 each element as argument。
原则上应该还是要这么写，这是最原始的方式，这是最原始的做法。然后用 underscore， 我想这个用 underscore 怎么写？
或者是括号。
好像不是括号 underscore， 应该不是这样子。Scala 的 underscore 的语法有的时候我也会弄糊涂。还是差点下了，反正这样子和这样子肯定是没问题的，这是没错的。用 underscore 的话，你可能要试一下看哪种 underscore 的方式是对的。OK， 我这儿我有点糊涂。OK。
还有一个问题就是HDFS 还有两种那个 file path， 一个是 file dot slash
file 不是 HDFS 的 ，file 是 local file 的，对。
还有一个是那个 URL 的 HTTP 那个 file， 这个不一样的是什么？就是
HTTP 的。你说 HDFS 吗？
对对对。
HDFS 的话是说这个 file 是在 HDFS 上，它会去 HDFS 去拿数据的。file 的话是 local file system， 不是在 HDFS 上，是在你的本地。
HDFS 就是说它是一个 URL， 就是说它是一个。
也不能说 URL， 是你的 HDFS 的那个地址。对，是因为你 HDFS 的话是要给出一个应该叫 URI 吧，给出一个地址。然后你的 file 这边其实是一个 URI 嘛，这是一个 unique resource identifier， 是给出一个在你的本地那个地址。然后它通过这个去区分说
我是去你本地拿呢，还是去 HDFS 上拿？
但如果只是一个 URL 的话，你怎么知道就是我去那个 URL，它怎么知道怎么 distribute 去那个各个 local 后 local nodes去那些？
这是 HDFS 的功能，它是把这个 job 是 pass 到 HDFS 上，而且底层是基于 HDFS 的。
所以就 configure 这个 file 会有那个 parameter 告诉他去怎么去那个所以他只要
你说 HDFS 怎么去那个？那是 HDFS 的整个那个 distributed file system 它的功能，它是相当于是把底层给你抽出来了，你不需要管它是哪个文件哪个是存在哪个节点上，这不是文件，是哪个文件的哪一块存在哪个节点上。其实每一块都分了好几块，复制了好几块。怎么去拿去哪儿拿的话，我们是不知道的，是 HDFS 在控制说我去哪儿拿这个数据，它要不停的去跟底层去看说 ，OK 我的要数据了，因为它要记录一下我的数据是在哪个机器上，它有一个那个 log file，对 HDFS 没讲 ，HDFS 后面再讲一点，我再讲 HDFS 没讲，然后。他会去，还会定期的去跟每个 node 去 communication， 去说 OK 你现在是不是还是 active 的，你数据是不是 available 的？如果不是的话，他会想办法说从别的地方再把这个有那 copy 再 copy 过来，或者说我再去别的地方要数据。反正底层是有一些相关的机制，然后你只需要告诉 HDFS 我要这条数据，然后 HDFS 就会自动去查说这个数据在哪儿，然后再给你。
一般我们做3的时候，现在都是 local host 做
其实这就是个 parameter， 其实无所谓，你是用 file 还是说用 HDFS， 这个不会影响结果，这只是说影响说你的 IO 是从哪里来的。
它其实就是一个 software，然后再加一个 table， 然后去说记录你的 node 是
简单的不能说是个 table， 但是它有一个 log， 它是 log， 算是一个 log。那除了这个记录说哪个节点的时候，它要记录各种操作。你的新文件来了，我要知道这个 block 怎么分配，对吧？还有一个 block 的一个表。人的话，还有它记录说各种相关操作，比如人有插入、删除、没啥，然后更新，你的这个都要记录下来。然后它定期的时候把这些 log 要给做，因为你 log 一直会变大嘛，然后定期的再做一些相关的操作去减少 log 的大小之类的。HDFS 会在后边给一个 brief introduction， 之前本来是想跟 Properties 讲完之后讲 HDFS， 但那次讲的比较慢，所以 HDFS 没讲完，所以就放到后面去。
但它不一定要是 local host， 可以是其他任何一个地址。
可以。当前我们是用的是 local host， 是因为我们现在测试的时候在我们自己电脑上装的。如果你用一个 cluster 的话，你当然是给那个 cluster 那个它的 URL 去做，就是 HDFS 是配置在那边。
就是这个地方，这个是相当于就是说这3个表左外连接吗？就是这个还有这个。
对，就是3个表，一个是 vertex 表，它其实是2个 vertex 表加一个 edge 表，然后做一个 join。
然后再跟另一个再做一个。
对，分别是说我这个 edge 的 source 跟你这个表的这个 ID 是一个，然后我这个 edge 的这个 destination 跟这个表的那个 ID 是一个，然后你把它们撞在一起。
是这样子。
对。
那个就是我刚才看了一下那个 project
这是第2个问题。
对，就是第一个应该不用那个 GraphX 那个。
第一个我不让你们用 GraphX。
我觉得也不用。然后那个
有人可能会用。
就不让用是吧？
对，就是不好用，因为 GraphX 会比较简单一些。因为 GraphX 有些 operator 它会帮助你来做这个事情，所以我就尽量说，第一个是用 Spark Call 来做 ，Call 的 operation 来做，这样会。
Spark Call 就是正常的那些。
对，就那些其实是 table operation， 会复杂一些。
我感觉这个就跟最开始就是这个例子前面讲的那个例子差不多似的，就是只要在后面加一个1，然后再 reduce 再 key 一下，就是那个。
对，其实差不多，但主要还有一些 sorting 的问题，就是主要还有一些 sorting 的问题，比如说排序。
的问题是吧？
对，sort 的问题。
就是按照这个排序从大到小。
我这还没说完，其实这个有可能 average value 是一样的，我还得在node ID 的排下去，这个忘写进去了，我得到时候再更新一下。
是
就是它有可能是说，2个 node 它的 average length 是一样的，一样大小。
对啊。
这时候还得按这个 node ID 再排下去。
然后再按照 node ID 谁大
再排一下，
谁往前排，谁小
对，这个忘写进去了，所以我到时候还得更新一下这个忘了。
明白了。
对，所以就还是排序的问题在里面，稍微复杂了一点。
然后这个是不是要用那个 GraphX？
对，这是用 GraphX 来做。这个会复杂一点。
我感觉这也复杂一点。
但我们想用这个分值是不是合理？因为之前那给了15，这给了10，似乎可能需要更新一下。好像这个复杂一点，那个简单一点。
我感觉，反正是这个看起来目前是有思路。
这个暂时还没有是吧？
对，
这个的话你就需要用 Prego 来做，因为它那个需要去拿到它所有的那个 reachable 的 node，这是一个迭代的一个过程。你只做一轮的话是做不完的。 对
又要迭代是吗？
对，这你不迭代的话是做不完的，你只做应该是做不完的。
哦，那个就比如说给一个 t， 比如 t 是1的话，但是看1能到哪些点的总数。
对啊，你一轮的话它只能到一个嘛，
这儿，
对
然后它也能到这儿，能到这儿。然后能到这儿，这是4个点，但是1它自己还能回来，这它自己算不算？
哦，回来的时候，哎呦，对，这个回来的算不算是吧？那我这也说明一下。
因为我刚才你下面给 example 说，如果
给的是0，对，0的话是4，对，1的话应该是4还是5是吧？
那0的话它自己也能回来呀，就是这样它还能
也能回来是吧？对，没错。
对啊。
那但是这个不影响你的操作，你只是说到底是算的时候算它还是不算它而已。对具体操作没关系。
加一不加一的事。
有道理，这个我再更新一下。做出的时候没想到这一点。
那就是这个得用 graph 来做。
可能这个更复杂一点，我可能把这个分值提高一点。第一个可能简单一点，分值再减少一点。
那我知道了。目前主要是这个还没啥思路。
因为刚学那个 Prego 的东西嘛，一会儿给你们看一下 Shortcuts Prego 怎么做的，可能会好一点，但可能还是会有点晕，因为 Prego 这一块的话本来学的就不多，主要就是说我说明3个东西，一定要定义3个方式，如何接收消息，如何计算，如何发消息，把这3个方式计算好之后，然后剩下就是 Prego 在帮你做。
是哪3个方式啊？
就这3个，这个是触屏的。这3个方式，就是第3个 parameter
就是这3个方式。
对，能把这3个方式定义好就可以了。
这个是发的，这个是帮着计算的，这个专门定义的。
那是接收消息。你看 Shortcuts 的例子的时候会看到这个。
那个小问题就是那个，你刚才说那个，如果你第一个 list 没有发过去，它会把那个 second list take， 然后当做一个
parameter。
我没听懂那个什么意思。
就是这儿，你再看这个例子，就是说，比如说这里嘛，对吧？这里的话，这个 function call 的话，其实是缺失的嘛，它只给了一个 n 的顶，只给了一个 n，所以它第2个其实是没有的。对吧？没有的话，那就是这个 x 去哪儿拿 ？x 就当成一个参数了，就当这个函数的一个参数，然后再就去外边拿，然后它现在是放在这个 filter 里面，所以这个 list 的每一个 member 都作为一个参数传到这个里面去，然后去算。
这个跟那个什么，就是不是第一个 list 是包含着所有的全体的信息，还有你的 max iteration 这些东西，也是跟那个有关吗？
跟哪一个？
对，上一页。他说 the first argument list contains figuration including the max number of iterations。
这是他们默认值，倒跟这个没什么关系。就是说 Prego 用的时候也可以像这样一样用。一般来讲 Prego 用的时候，你要把所有的参数都给全嘛。但是有的时候你可以不给全，你只给前面这些，后边的不给。后边这个去哪儿拿呢？是去当做参数了，因为是前面可能是类似于这种。就是你可能是有一组的不同的操作，然后这一组不同的操作去发给这个 Prego 的 operator 去做，让它这样做不同的状之类的，就是大致是这个意思。不过你一般来讲，我们一般来讲不需要去搞得那么复杂，我们都是把所有的都给全就好了。
Okay, so let's continue about how to use a Prego operator to do the single source shortest path computation. These codes are just get from the Spark GraphX homepage, so you can click this homepage to see more details. And there's another implementation. This implementation is, I think, is more clear because it separates all the operations. So the key part is that remember that in GraphX, what you need to do, you need to define the 3 operations: how to receive messages, how to merge messages or do the computations, and how to send messages. And in the single source shortest path problem, well, from the perspective of each vertex, what we need to do is that so each vertex will receive some messages, will receive some distances from the incoming neighbors, right? So that's from his neighbors, and it assumes that the incoming neighbors has some known distances, and the distance of the neighbors plus the edge distance will be the possible distances of this node, and it will compare all the received messages and select the smallest one as the distance of this node. And then based on this result, it will also send this updated distance out to its outgoing neighbors, right? So that's the whole idea. But how we can split these operations into the 3 functions, it is like this. So first we need to define a vertex program, how to receive the messages. And the vertex has an ID and existing distance, and it will receive a new distance. Okay, and then it will compare the 2 distances. So which one is smaller? So that's for this part. It will check the existing attributes and the new attribute received by the messages, and then decide how to do the updates for the existing messages. So so the node will keep the smaller one. And the merge messages here is to do the merge for all the messages received. So remember that one node has multiple incoming neighbors. The possible distances can come from different sources, right? But for all these messages, in fact, we only need to keep the smallest one. So this is a merge message. So if we have multiple messages, we use this function to do the merge. We always select the smaller one. We always select the smaller one. Then all the messages will be merged as this new dist actually. And this is about how the vertex will receive the messages and process the messages and merge all the received messages and only select the smallest one and compare with the existing one to keep the smaller one between the existing one and the new attributes, new distance. Okay, so now assume that this node has a new distance, right? So it will try to check if I need to send my message out. How to do that? There's a triplet. So for this triplet, it will check for the source attribute, so it's just one edge, plus the triple attribute, which is the edge attribute. So the incoming neighbor and the edge to the destination. So it will compare if the source attribute and the edge attribute is larger than or smaller than the destination attribute. If it is, which means that this is update, right? And if there's update, So I need to send my message out. So there's a operator operation. So it tells that I need to send a message to this destination node. For this destination node, what I need to do is to give the destination node a new distance. So this is a distance computed from my part. And if there's this condition is not satisfied, then this is just empty message because there's no update. If there's no update, I don't need to send message out. So this is about 3 parts. So the full Prego operator function call is like this. We remember that we also need to do initialization. So there's an initial graph. If ID is a source ID, and the distance will be initialized as 0. Otherwise, it is initialized as infinity, the positive infinity. So see here, we use the map vertices. Okay. Previously, each ID, each vertex has one attribute, but now we need to update their attribute, the distance attribute. So we use map vertices, use this function to update their values. And how to update is like this. Only the source node is his distance is updated as 0. Others will be updated will be initialized as a positive infinity. So that's for initialization. And next we will call the Prego operator. So this is initialization. It's an initial message. And then this is the first parameter. Others are by default, such as maximum number of iterations and the active directions, just according to the optical neighbors. And this is the second parameter list. This one is the vertex program here. This is the vertex program. Tells how to receive the functions. And here is how to send messages for each node. And they will check the triplets and see if on this triplet there is an update need to be, there is an update. If there is an update, some messages will be sent to this destination node. And this is to do the merge, the message merge. When one node receives some messages, it will do the merge according to this function. Okay. And finally, you can get the shortest path. And there's some also some termination conditions. So the full code is, let me check if it can clear. There's no internet connection, right? Oh, here. Hey, why? What's wrong? It's weird. The full code is here. Yes. As you see, you can see the initialization and how to call the Prego operator. And finally, you can print out the results. And you can run the code here in your Spark installation folder. So in your Spark installation folder, you can go to this position to check the source code for this single source shortest path problem. And this is another example, another implementation. So finally, they also use Prego operator and some parameters. The vertex program, sending messages, and how to do the merging. This is a little bit more clear because it separates all the operations. Okay, you can try to read the codes later. And so this for the Spark GraphX part. In the second project, and you need to use this Prego operator to solve the problem, because otherwise it's not very easy to get results. So in that problem, you are asked to compute the number of nodes that are reachable from given source node. So use GraphX. Actually, it can help you to solve the problem efficiently. But I know it's a little bit difficult because it seems very complicated, right? And it's better you try to find some more examples for using Prego on the internet than to see how to solve that problem. Okay. For the rest part, we have only about half an hour, so I'll try to go through them very quickly because they are very easy to understand. And so this part is called Spark SQL and data frames. Spark SQL is actually initially it is not Spark SQL, it's called Shark, and it's aimed to provide some secure APIs in Spark for the data analytic, for data analysis to do some kind of data analysis jobs. And the idea is to transform the RDDs using SQL, and the data source can be from different sources, such as Hive or JSON. This should be familiar with you, right? Just JSON format, data type. Remember that Spark SQL is not about SQL actually. It aims to create and run Spark programs faster. It's not SQL. And the early version is called Shark, but now it's already been subsumed by Spark SQL. It's not called Shark anymore. So Shark modifies the Hive backend to run over Spark. We haven't learned Hive. Hive is kind of a SQL-like language over MapReduce. So in Hive, you can write SQL-like statements to create tables, to do search by using the select from where clauses, and do a lot of things that you can do in relational database. So Hive, the objective of Hive is also similar to Spark SQL. Try to let the users who are not able to do MapReduce programming also be able to use MapReduce. Okay, it provides a SQL-like APIs for users to use, but in the lower level, they are compiled to MapReduce jobs, and that's about Hive. And Shark, the early version of Spark SQL Shark, is modified the Hive backend to run over Spark, but there are some limited challenges. First is about limited integration with Spark programs, and also about optimization, because it tried to integrate a Hive backend, but the problem is that the Hive optimizer is not designed for Spark, it's designed for MapReduce, so the performance is not very good. So now Spark SQL borrows Hive data loading and in-memory column store. These are ideas borrowed from Hive and some other and in-memory column store system. And it adds a RDD-aware optimizer about optimization, or much richer language interfaces. You can use Python, Scala, and Java to do these things. And Spark programming interface with Spark SQL can be like this. So Spark is based on RDD, and now you can use Java, Scala, Python to write Spark programming, write Spark programs, and you can also use Spark SQL to contact with the Spark call. And here, what we will learn is about the data frame API, and lower level is optimize data frame API. And then upon Spark SQL, we can use JDBC or the console to interact with the Spark SQL to do the data storage and do data search. In Spark SQL, the most two important concepts are called data sets and data frames. And a data set is a distributed collection of data. It provides the benefits of RDDs with the benefits of a Spark SQL's optimized execution engine. I don't want to go into much details because it's a little bit complicated. Just remember that so data set is a distributed collection of data, and data frame is a data set, also data set, but organized into named columns. So data set does not have named columns, but data frame has named columns. So in Scala and Java, so data frame is represented by a data set of rows. So which means that in programming, you just use data set row to represent the data frame. in Scala, also dataset row to represent the type of data frame. And what we always use data frame, but we will define data frame by dataset. So that's the idea of introducing the two concepts. The difference between them is that between data frame and RDD is that so data frame is more like a traditional database of two-dimensional form. It's like a table with columns and rows, in addition to the data, but also have the structure information of the data. It's kind of a schema. So for example, if we have a person class or person object, person data, if you represent the person as RDDs, and for Spark, it's like this, it does not know the details of person. So we don't know the members of this person object. We only know, okay, so this piece of data is for person. But in data frame, if you use data frame, so Spark is able to know the detailed structure information. It's kind of a schema. I know that, okay, Spark knows that there's name, age, and height in this person object, the string, int, and double. Okay, so that's a major difference between RDD and data frame. So which means that now RDD provides you more, because it provides you more detailed structure information. And as a result, so Spark SQL can clearly know what columns are included in the dataset, and also the name and data type. And as a result, so Spark SQL, Spark SQL, can have much more target optimizations to improve the efficiency. And the data frame can come from different sources, such as JDBC, JSON, and external can also be from CSV, and HBase, and Cassandra, and some other relevant systems. In order to use Spark SQL, it's just like write a Spark program. But you do not create a Spark context object, but instead you create the Spark session object. And it's similar to the Spark context object. It's also used to connect your program and the cluster. But here, the configuration is a little bit different. You don't need to set the master because Spark SQL has its own cluster manager and so builder, and give an abstract name, and the configuration is so you can list a lot of configurations here, and then create, get, or create. So now you create this Spark session object. So next, now you can use these Spark session objects to do various operations. So Spark Session in Spark version 2 also provides a built-in support for Hive features. So you can also write queries using HiveQL, and also access to Hive the user-defined functions. But we don't need to know if you don't use Hive, so this is not very useful to you. Just remember that if you want to use Spark SQL, you need to create Spark Session object first. So after the Spark Session object is defined, so next you can create data frames, or you can think of this like creating tables in your relational table. If you treat this Spark SQL like a relational database. For example, here we read a JSON. So this is a people JSON input file. So we read the JSON input. This is a Spark context object, remember, okay? So we use this Spark context object to read this JSON file. And next, we can use the functions provided by this data frame. So this is a data frame to do various things, such as show. So we can show a table to you, actually. We can see there's a column name and the random values. We can also have null values because for Michael, we don't have a value for his age. So it's null. It just like a table. Then next, for all kind of table relevant operations, you can use by using data frames. So this print schema that will tell you what is the schema like, age, name, and data type. And we can also just select some columns. So this is select name, given the column name. We only select the name column, 3%. And here are some other operations. So select name, age, +1. So we get actually we get a table and have the names and their ages +1. But this is null, so it is still null. or we want to find people older than 21, so we have a filter age larger than 21, so only ND is returned. And we can also count people by age, so we can use group Y. And we group by age, so for each age, we can count number of person who have this, whose age is of this value. So that's for group Y. So you can see that in relational database, many relational database relevant operations are supported by the data frame object. So you can use the data frame object APIs to do these things. And you can also run SQL queries by using data frame. So we create a SQL data frame, or Spark SQL, and we can use this to wrap SQL statement, such as select star from people. So everything will be selected in the table. Now, we do this, and the result will be stored in this SQL data frame. So this is a SQL statement, and the result is a table, right? Then the table will be stored as a data frame. So later you can use show or some other operations to operate the table. So here is the result. And there are many examples available in this page. So you can see the full example code in this link. For the Spark SQL, as a site, it's mainly used for structured data, and also for the people who are not quite familiar with Spark Scala programming. So now if we are able to format your data as a tables, right? So it's just kind of schemas, relational data, structured data. So now you are able to use Spark to do the jobs very easily because you know SQL, and you just need to learn these very few operations. Then you are able to do the data analysis based on the SQL statements because you can wrap them by using the data frames, right? It's very easy. Okay.
When should I go to Spark SQL or Hive?
Hive is based on disk. Spark's SQL is based on memory. So the data are stored in different different positions, right? So Hive is based on MapReduce, but Spark SQL is based on Spark. Okay. So according to my experience, recently I talked with one of my friends working in a big company. They use Hive, but not Spark SQL. I asked why, because they said their data is too huge. It's not able to hold all the data in memory. And they are not doing real-time jobs. They just want to get the daily statistics so that they can just use Hive to run the jobs. So every day they will get some results, that's fine. But they're not doing some kind of real-time queries. If you think that you need to return the results very fast, then you need to consider using Spark SQL. But again, the data can't be too large because they told me that their company is, their data is really too big, so Spark SQL cannot be used. Okay, so there's the last part about Spark streaming. This is also relevant to next chapter because next chapter we will learn streaming data processing, but not directly connected. Okay, but they're both on streaming data processing. In this part, the objective is to deal with streaming data, which means that data is not static. Okay. Nowadays, actually, many important applications are processing the large streams of live data instead of the static data, because every day the data are updated. For example, in social networks, right? So Facebook, Twitter, every day they will receive many new data generated by users, and or some such as Google also every day has a lot of new query logs. So for these applications, if we want to do some statistics over the streaming live data, while using the existing platforms will not be suitable. They are not competent to do such kind of things. Because distributed stream processing framework need to do the following. They must be able to scale to large clusters and achieve low latency, which means that they must do solve the problem in a few seconds. But for MapReduce, definitely it's not able to do this. And Spark is better, but Spark, what we have learned, Spark Core is also not designed for for streaming data. So the efficiency is also not very good. And so as a result, so Spark, this project, began to design this component, Spark streaming component. It's an extension of the core Spark API, enables scalable, high throughput, and fault-tolerant stream processing over live data streams. And the Spark streaming can receive streaming data from different sources, such as Twitter, and these are also some other streaming data sources. And by the Spark streaming processing, then we can store the results to such as HDFS or to relational databases or to some other places. So Spark streaming is kind of the computation is kind of like running a series of very small and deterministic batch jobs. Although it's streaming data, but we will split the streams into several batches, and we process each batch in parallel. So we will chop up the live stream into some batches according to time, maybe 5 seconds, one batch. So within these 5 seconds, according to the data I received, I will create one batch. And the Spark will treat each batch of the data as RDDs and process them using the RDD operations. And finally, the process results of the RDD operations are returned in batches as well. So it's like this. So this is input data stream, right? And this Spark streaming will chop the stream to batches. And for each batch, we use the RDD to represent this batch. And so the Spark engine will be able to process these batches, and we can have batches of result as output. And for the Spark streaming model, it uses D stream called discretized stream as a major data object. And it represents a continuous stream of data. And it can be created either from the input data streams or by applying the high-level operations on other D streams. So just like RDDs, but it's a streaming RDDs. So internally, one data stream, a D stream is represented as a sequence of RDDs. So now you see it's this stream actually is just a sequence of RDDs. So all the operations for RDDs can also be used for the D stream because it's just a sequence of RDDs. And the APIs are also very similar. And we can do, so I give you an example about how we can do this streaming word count. In word count, we do the count for the word frequencies in a static file, right? Giving you a static file, you count the number of words. And the streaming word count is to do the word count in a streaming manner. So within some time period, we count the number of words in this time periods I received. So the program code is like this. Instead of using the Spark context, we use the streaming context to create an object. And this will connect our applications and the cluster. So the configuration is also the same. We need to set master, and we also need to set application name. And next, by using the streaming context object, we can process and receive the data. In this example, it received the stream from the socket from port 49 in localhost. And okay, so in this time period, I will try to process all the text received from this port. And what we do are just like word count, right? But here it's different because that I define seconds 10. So which means that I will return result every 10 seconds. And the result is about, in this 10 seconds, how many words are received. And next, after these 10 seconds passed, so some new results will be generated. It is in the next second how many words are received in the system. Okay, so that's the idea. It's called the streaming word count. It's not on static data, it's on the streaming data. And then we care about the data within a time period. And so we use the streaming context to connect our application and the cluster. So next we will begin the job. So because we use streaming, Spark Streaming, so we also need to import relevant classes from Spark Streaming. And we need to create a local streaming context object here. The 10 seconds is used to specify that we'll do the count for each 10 seconds. You can give a larger value for this. The most important thing here is that in Spark Streaming, you need to use at least 2 threads to process the streaming data. Why we need to have at least 2 local threads? It is because it is streaming data. Okay, one is used for processing the data. Another one is used for receiving the data. If you have only 1 thread, so you are only able to receive the data, but you have no resources for processing the data. So that's a problem. And after the streaming context is defined, you need to do the following. First, you need to define input sources and where the input is from. So in the previous example, it's from the socket, from a port. Or it can also be from, such as from Twitter or from other sources. And they will be converted to D streams. So remember that this stream is just a sequence of RDDs. And then we need to define the stream computations by applying the transformation output operations to these streams. And now, next we need to start the job, right? So we use Spark context start. We begin to receive the data and process data and wait for the process to be stopped, either manually or due to some errors using this await termination. We can manually terminate the program, or maybe the source stopped to sending the data to you, stop sending the data to your program, then it will also terminate. This is about the data flow of a streaming word count. So here is a major difference. Right? We do not use Spark context. We use Spark streaming context, and we use the socket text stream to create this stream. This is from socket. And next for this stream, remember this is not RDD, it is this stream. But all the APIs for RDD can be applied to the D stream as well. And that's similar to the word count, flat map, map, and reduce by key. And here we start the job and wait for termination. And you can also check the entire code in example here, and also try yourself. Next is about how you can submit your code to Spark. We can still use SBT to compile and package and submit to run our program. So we first use submit to compile our application as a package. And we also need to write a configuration file, but here it is a Spark streaming, not Spark call. So previously we used Spark call for the word count, but here it's a streaming word count. We use Spark streaming. We also need to give the version number. And we also need to define data sources. But here I will skip this because we will not use them in our lab and also in our course. And in order to run the streaming word count, so we can use this comment. So this is a netcat small utility tool in Unix-like systems such as Linux. So you will open streaming actually. You will, so this program will get the input and send your input to this port. And which means that now your program can begin to receive the data from the input. So after you input some data by using this comment, and your application will receive this data and then do a streaming word count every 10 seconds. This is an example. So for example, here we use NC LK for 9, and we do some hello world, hello world, hello. You can try to type as many times as you want. And the result will be like this. So you can see in the first 10 seconds, nothing is received. And then in the next 10 seconds, it receives one line, 2 hello, 1 world is this one. And in the following 10 seconds, it receives 2 lines, 2 hello and 2 world. So the result is like this. And just streaming data processing. Okay. I plan to show this to you, but also again because of time, I don't have time. So I'll skip this part and to more detailed technical details. So as introduced before, this stream is represented by a sequence of RDDs. So this is the idea. This stream is RDD at time slot 1 and another RDD at time 2, RDD at time 3, RDD at time 4. And so the data from in different time periods will be put into different RDDs within the D stream. So next, all the operations work on D streams will be applied to each RDDs within the D stream, such as flat map or reduced by key, and some results will be obtained from each RDD and its operations. And so the input D stream, the D streams representing the stream of the input data received from the streaming sources, such as lines. The lines are received from the socket. And each such D stream, input D stream, is associated with the receiver object. So this is used to receive the data from the source and store the data in Spark's memory for processing. And so as a result, for this receiver, we also need to have a thread for this receiver. So that's why we have at least two local threads. We must give one local thread for this receiver. If you use local 1 as a master URL, now the problem is that the single thread will be used to run the receiver only. Okay, it will keep receiving the data, but there's no available thread to process the received data. So the word count will have no result. So you can, if you have time, you can try to test this by setting this local to only 1, not local 2. And when running locally, you always use local n as a master URL for the number of receivers to run, because maybe you have multiple data sources. If you have 2 sources, then you need to set local to at least 3, because 2 must be used to receive the data sources and 1 for processing the data, but otherwise you will have no results. And it's about the most important part in Spark data streams. This is another example from the getting some data from Twitter. So Spark also gave you a Twitter API for you to use. So you can use the Twitter utils to create a data stream, which means that, okay, my this stream is created from the Twitter data. And so now you keep receiving some data from Twitter. Okay, and now it's but the processing is also the same. So the received Twitter data are chopped into batches. So batch at this time t and time t plus 1, time t plus 2. And then they will be stored in memory as RDDs. And then for processing, for example, here we get a flat map. So each status is to get text. Then we, remember that this is not a real example. Okay, it's not run. You cannot run this directly. You need to do some kind of modification. These codes are just used to show the ideas. Okay, not a working example. So we get status, get some tags from the status. We get hashtags. Okay, and so this flat map will be applied to each batches. And this is a previous data stream, and now we get a new data stream. This new D stream, new D stream is used to store the hashtags. Okay, and now previously this tweet stream, and now it is hashtag D stream. We have new sequences for RDs. And next, these hashtags can be saved. So we can save as Hadoop files. We can save them to HDFS. Okay, and we can also save them to local file systems. So the batched results will be saved. We can also write to database and also to some other sources. And the next is about the window operation in the streaming data processing. So besides the time period, such as 10 seconds, you can also define a window operation. And this is a length